Most discoveries in the history of astronomy began with serendipitous observations, an unexpected speck of light appearing in an image, an anomalous date, a curve disrupting the calm. But this time is entirely different. The discovery we are about to discuss did not begin by chance. It originated from a deliberate hunt, a deep dissection of a known anomaly. What I present to you today is not conjecture, but conclusions grounded in cold data and rigorous mathematics. We tracked an interstellar visitor known as the Trident Map. Its name derives from its unique tripartite structure and map-like patterns on its surface. Over the past months, the global astronomical community has strived to understand its nature. Initially classified as another interstellar comet, similar to MUA we observed before, its behavioral patterns revealed peculiarities at every turn. Its light curve was irregular. Its orbital parameters defied explanation by pure natural mechanics. Thus, we launched an initiative, mobilizing the world's most powerful radio telescope array, accessing Gaia satellite's three-dimensional galactic map, and harnessing the immense computational power of supercomputers, all to answer a single, fundamental question: where did you come from, three-side net? The answer lies hidden within its path through interstellar space. Any object moving through the cosmos leaves a trail. Its trajectory is shaped by gravitational fields along its path, much like a ship leaving a wake as it sails the ocean. By tracing this path backward, we can deduce its origin. This sounds straightforward, yet in practice, it represents the pinnacle of celestial dynamics. We must account for the sun's gravity, for planetary gravitational perturbations, even the subtle influence of the Milky Way's immense gravitational field. This is a complex gravitational chain spanning light-years. Any minuscule error could lead to results widely off the mark. Yet, when we completed all calculations and cross-verified every data point, we arrived at an astonishing coordinate, a precise origin pointing deep into space. The data reveals the three-side map did not originate in random interstellar space. It comes from a specific star system. Its conclusion isn't derived from a single model. We employed three entirely independent computational methods for cross-validation. The first is direct numerical integration, precisely solving the equations of motion for objects within gravitational fields. The second is the Monte Carlo method, using millions of random simulations to identify the most probable path. The third incorporates machine learning algorithms, enabling AI to identify the most matching trajectory features from vast stellar datasets. These three methods, designed to operate independently, yielded a completely consistent conclusion. Such convergence carries immense weight in science, signifying exceptionally high reliability. This is no coincidence, no error. It is fact. The fact being, the three-side map originates from a place it shouldn't exist. More precisely, its trajectory indicates it was not randomly ejected. Its method of departure, its initial velocity, its navigational precision, all point to an origin our current knowledge cannot fully explain. Before delving into that unsettling origin, I wish to first show you the trajectory itself, to see where mathematics leads us. This retrograde path takes us to a neighboring region of the Milky Way, approximately 270 light-years from us, calculated at the observed velocity of the three-side map. This journey consumes nearly 2 million years of its existence. When this object began its epic voyage, our ancestors had just mastered the simplest stone tools. Earth was in the climate-volatile Pleistocene epoch, yet it had already commenced its long glide through the interstellar medium. 270 light-years sounds unimaginably distant, but in a galaxy measured in tens of thousands of light-years, it is merely a stone's throw away. Like the difference between traversing 3 city blocks and crossing an entire continent. This visitor hails from our cosmic neighbor, yet this neighbor sent us something. Something that took 2 million years to reach us. And now we discover its arrival may not have been accidental. Next, we will examine irrefutable trajectory data, see how it challenges our ingrained perceptions of the cosmos. We have uncovered something that should not exist. And this is merely the beginning of the story. To grasp the gravity of the 3-I chart's origin conclusion, we must delve into the core of its data analysis. This is not a fleeting glimpse from a single telescope, but a global collaborative research project, whose analytical complexity and rigor are unprecedented. The computational core was led by Sarah Chen's team at UC Berkeley. They inherited an exceptionally precise yet seemingly contradictory set of observational data. The 3-I map's trajectory broadly conformed to celestial mechanics, yet exhibited inexplicable micro-adjustments at the microscopic level. The team's first challenge was retrospective calculation, distinct from predicting known celestial bodies' future paths. Retrospection meant tracing backward through millions of years to identify the most probable starting point. This required viewing the solar system and its surroundings as a dynamic gravitational network, not the static backdrop. Their first approach employed direct n-body numerical integration, an intensely computationally demanding yet fundamental method. It simulates the continuous influence of all significant gravitational sources encountered by the 3-I map during its flight, including the historical gravitational effects of the Sun, planets, and even nearby stars. Through reverse integration on supercomputers, it gradually traces the path back to the journey's origin. The second method employed Monte Carlo sampling, a powerful tool grounded in probability theory. Researchers established millions of initial conditions for the 3-I spectrum's potential departure, including varied starting positions, velocities, and times. These were subjected to forward flight simulations within the Milky Way's gravitational field, ultimately filtering out trajectories that could precisely reach our solar system today. This approach avoids reliance on singular initial assumptions, instead letting vast simulations speak for themselves through data. The third approach is the most innovative. They introduced machine learning algorithms. First, they trained data models using known natural interstellar object trajectories, enabling the AI to learn trajectory characteristics under natural ejection mechanisms. Then they fed the 3-I star chart's trajectory data into the model for analysis. The AI's task was to assess how well this trajectory matched natural trajectories and identify the most probable region of origin. These three approaches stem from distinct philosophies. Direct integration relies on deterministic calculations based on first principles. Monte Carlo employs probabilistic simulations grounded in statistics. And machine learning utilizes pattern recognition based intelligent filtering. Together, they form a mutually validating triangular fortress. When three independent teams ran these algorithms separately, a startling phenomenon emerged. The optimal solutions produced by all three supercomputers overlapped perfectly within the margin of error. They all pointed to the same celestial region, the same distance range, the same star system. Such a level of convergence is extremely rare in science. It means the conclusion is almost impossible to attribute to coincidence or computational error. This locked in origin region lies 270 light-years from Earth. Based on the ultra-high precision 3D map of the Milky Way provided by the Gaia satellite, we can compare this region with the known star database. The results clearly show the presence of a star system named HD 43782 within this region. Let us examine this potential home more closely. HD 43782 is a G-type main-sequence star, with a spectral type identical to our Sun. Its mass is approximately 1.3 times that of the Sun. Its surface temperature differs by less than 200 degrees Celsius, and its age is about 4.8 billion years, remarkably close to the Sun's 4.6 billion years. Physically speaking, HD 43,782 is nearly the Sun's twin. If you stood on a planet orbiting it, the Sun you'd see would be indistinguishable from what we observe from Earth. This similarity immediately sparked immense interest among astronomers. Next came verification on the time scale, based on the calculated flight velocity from the retrograde trajectory, and combined with precise distance measurements. The 3-side map completed this interstellar voyage in approximately 2 million years, a thought-provoking span of time. 2 million years ago, as this object departed its home, Homo erectus on Earth had just begun crafting simple lean hand axes. Continental plates occupied slightly different positions than today, and an ice age enveloped the northern hemisphere. Meanwhile, an interstellar object had embarked on its arduous journey. A distance of 270 light-years seems insignificant on the scale of the Milky Way. Our galaxy's disk spans roughly 100 light-years in diameter. This journey equates to traversing merely 3-thousandths of the galaxy's diameter. It's akin to traveling across an entire country, yet moving only 3 city blocks. This visitor truly hails from our immediate neighborhood, yet it is precisely this neighbor that has sent us something profoundly unusual. Each step of the data analysis underwent rigorous scrutiny. Every link in the chain was meticulously crafted for flawlessness. 3 independent analytical pathways ultimately converged upon the same conclusion, compelling us to confront its profound implications. The trajectory itself narrates an extraordinary tale, yet what lies ahead are the even more counterintuitive details within this path. Once we accepted the fact that the triple-I spectrum originated from the HD 43,782 system, a deeper and more unsettling question surfaced. Did its journey itself follow purely natural laws? The details revealed by ballistic analysis began to challenge the limits of our understanding. What first aroused our suspicion was its method of ejection. Interstellar objects in nature typically originate from violent dynamical events, such as chaotic collisions during planetary system formation, or ejections of Oort cloud material triggered by stellar gravitational perturbations. These events are characterized by randomness and non-directional dispersion, like shrapnel scattering in all directions after an explosion. Yet the 3-side map's trajectory data paints a different picture. It was not randomly ejected from the HD 43,782 system. The data indicates it departed from a highly specific location.